repeat this example, remember that this problem was from 0 to infinity dx over x squared plus 1, and we use z equals x plus iy, and dz is equal to dx in this case. And now we learned that in this px over qx type of integrals, the degree of the denominator should be more than twice the degree of the numerator. And also another condition that we have to have is that any of these poles which make denominator to 0, okay, cannot be on the real axis, because the method requires drawing this semicircle and then increasing its radius to infinity to cover from minus infinity to infinity. And then obviously the result is just 2 pi I total residual. Okay, so in the first example, we just see that there is nothing on the top, and the degree of the denominator is 2, but the integral is not from minus infinity to infinity. So we make it from minus infinity to infinity by dividing by half, because the function is even. So when you have negative x values, also it doesn't change any sign. So for these kind of functions, we have the right to do this. So we calculate this twice as much and just divide it by 2. In this case, z is taken as x plus iy, and obviously dz will be equal to dx. So each dx, so dx that you see here can be replaced by dz, and of course x is just z, okay? X is just z, okay? Good. So z squared plus 1, okay? Z squared plus 1, and because we don't have any y or something like that, so this term does not exist, obviously. Okay, so we have z squared plus 1 on the denominator. Okay, and then now this is written as z minus iz plus I. Okay, in this case, we know that this is the problematic root, or just let's say the singular point. Why? Because one of the singular point is here, the other is there, this minus I, but it is included only in our curve. Okay, the thing which is included is the one which is above the real axis. So this is the one which has some property of letting us to use the residual. So we get rid of this term, and then the rest of the function is calculated at this singular point, and then the result is just 1 over 2i for the residual. Okay, after residual is obtained, we multiply it by 2 pi I, but we shouldn't forget 1/2 in the here 1/2. The 1/2 is there also. So 1/2 times 2 pi I divided by 2i. These cancel, and 2 is also canceling, and the result is just pi over 2. Basically, we see that from 0 to infinity, dx over x squared plus 1 is equal to pi over 2. So the result is really obtained by using this complex analysis. Okay, so this is real good method. Okay, now we go to the second example, or let's just jump, okay, to another case. Okay. Now we start the Fourier series. Okay, so the next objective of our course is the Fourier series. Okay, so Fourier series are written for functions which have this kind of property. Fx plus period is equal to f of x. So this means that periodic functions, okay? Periodical functions. So for periodical functions, we can use Fourier series. So what kind of functions are they? Sinusoidal, okay? Or just, this is also some kind of periodic function. So it's all like square, also square wave like this, okay? These are all periodical functions, okay? So what we do is that the function is expanded into the Fourier series like that. F of x, any function, is like a0 over 2, which is constant, plus the sum n equals 1 to infinity, an times cosine nx plus bn times sine nx. Okay, so in this case, an and bn are defined as this: a0 is equal to 1 over pi integral f of x dx from minus pi to pi, okay, and an is 1 over pi integral, okay, minus pi to pi f of x times cosine nx dx, cosine nx dx, and bn being equal to 1 over pi from minus pi to pi, okay, f of x sine nx dx, sine nx dx. Okay, so we have a0, an, and bn given by this values, but now we can also write this Fourier series by using the boxes. Okay, so instead of being instead of the function becoming periodic from minus pi to pi, suppose that the function is periodic from minus L to L. So this is minus L to plus L. This is usually the case when we have like quantum mechanics problems in which the waves are included in some kind of boxes. In this case, the same function now can be written as this. F of x is equal to, again, a0 over 2, but now the integral from n equals 1 to infinity, okay, from 1 to infinity, an cosine, not nx, but just n pi over L x, plus bn times sine n pi over Lx. As you see, at L equals minus pi and pi, okay, this is exactly the same as this, okay? So this cancels L on the denominator. So this can be used, and the coefficients are given exactly like this, but the limits now, for all the limits, will be from minus L to L, okay? So all the limits will be taken like that for L. So now there are some properties of this Fourier series. If the function is even function, which is that if you replace x by minus x, the function is itself, it means that it's even. Okay, in this case, we see that bn will be 0. Why? Because bn is just the function times the odd function, sine nx. Sine, this is odd, don't forget, because sine changes sinusoidal function changes sign when you replace the argument or the angle by minus of that angle. So if you replace x by minus x, it becomes minus, right? That's why this is an odd function, but cosine is an even function. Now, as you see, f of x is multiplying these even and odd functions. If f of x is even, then even times odd is also going to be even, odd, but even times even will be just even. That's why for the even functions, okay, bn will include here the odd function, so which will be 0, but this one will not be 0, okay? This one will not be 0. So in this case, an will be equal to, okay, an will be equal to from 1 to L, from minus L to L, okay, f of x times cosine x dx. But instead of this, we are writing now from, okay, since we are using this form, not L form, okay, from minus, okay, 1 over pi minus pi to pi f of x cosine over that. And then now, since this is symmetric, again, the even function, then we can write it as from 0 to pi and, okay, 2 over pi, okay, the result will be just, so it's just twice as much. So from 0 to pi integral is twice as much the integral minus pi to pi because of the property that we had talked earlier, okay? So basically, this is what we will do. So we will just get f of x cosine x dx, okay? For the even functions. For odd functions, okay, this is for even functions. For odd functions, in this case, a0 and an will be equal to 0, but bn will survive. Bn will be just 2 over pi from the 0 to pi, okay, f of x and sine nx dx. Okay, so this will survive. Now let's give an example. In this example, we have now the function given as square wave, okay? So it goes like that. So it jumps to plus and minus values, okay, systematically, and the period is the same like that, okay? Sorry, this part will be like this, and then here, okay, like that. It's like the square wave, as you see. It's just a square wave. Now, the property is that this x is changing from 0 to pi here, 2 pi there, and we know how to calculate the period. This is minus pi, minus 2 pi, and so on. The height of this thing is k, and this is minus k, obviously. So this can be written as just written as some kind of function which gives you plus k or minus k depending on in what interval you are in what interval you are. Okay, so now we can define the function like this. This function, okay, is equal to minus k between minus pi and 0 and k between 0 and pi. Okay, 0 and pi. So now the question is find Fourier series of this function. The question is that. So first we have to get a0. a0 is equal to 1 over pi, okay, minus pi to pi f of x dx. But now there is no function but just the value from 0 to pi. Now this function has two values from, okay, minus pi to pi. In some of the interval it's minus k, and the other interval plus k. So this interval can be divided into two different integrals, okay. One from minus pi to 0, okay. In this case it's minus k times dx, and then the other one from 0 to pi. In this case the value is just k times dx. And this, as you see, this is a very simple integral, and this happens to be just 0. It gives you 0 if you just solve it. Okay, this gives you 0 because this minus k times x, but the limit is minus pi to 0, and this one is kx, but from minus pi to 0, okay, 0 to pi, sorry, this is 0 to pi. So the upper limit is 0, but the lower limit gives you plus kx, but there is a minus sign, so this gives you minus kx, this term. But this one, the lower limit is 0, but the upper limit gives you kx, and kx cancels that, and the result is 0. So A0 is 0. If A0 is 0, then probably AN will be also 0. Okay? Because this is a not even function, this is odd function between minus pi and pi. Because it changes sign. So if this is odd function, we know that if this is odd function, A and A0 will be 0, okay, for the odd functions, and AN will be also 0, and let's see why it is becoming 0, okay. Now let's calculate it on the right side of this board, okay. So we just write AN as just 1 over pi, okay, from minus pi to pi. Again, we separate this region into two parts, minus pi to 0, okay, minus k, the value of the function between minus pi and 0 times cosine nx dx, and then the other one is from 0 to pi. In this case, the function is k times cosine nx again dx, okay? So we have this property, but now the integral of cosine is just, this is 1 over pi, okay, let's say k outside, it's minus sign, but the integral of minus cosine is sine nx over n, okay, and now the limit is from minus pi to 0. Similarly, this is just minus in this case, because the integral of cosine is minus sine, so minus sine nx divided by n, now the limit is from 0 to pi, okay. So as you see, in pi or minus pi or 0, sign just vanishes, and then the result is simply 0, okay. So now let's calculate Bn, okay. So Bn are, okay, these coefficients are 1 over pi, again, from minus pi to 0. We learned the technique now. We always take minus k in this integral, because from minus pi to 0, we have this property times, okay, sine nx, and then the other one is from 0 to pi, again, k in this case, sine nx again, okay? So dx, of course there is dx, right? You shouldn't forget dx, because this is the variable of the integration. So as before, this is a very simple integration. So we have k over pi taken outside, and okay, minus the integral of sine is just cosine, okay. Integral of sine is cosine with a minus sign, okay, cosine with a minus sign, but there is another minus, so it cancels that. So we basically get okay, cosine nx over n from minus pi to 0, and here, okay, we will have minus k, the k is taken outside, cosine nx over n, but now the limit is from 0 to pi, okay, from 0 to pi. If we put these limits here, okay, we see that it is equal to just 2k, okay, 2k over n pi, 2k over n pi, 1 minus cosine n pi. This is what we get. Okay, so when we use the lower limit here and upper limit there, we get 1, and then because there are two of them, it's 2. 2 is coming from there, okay. So and then the lower limits will have cosine n pi, but cosine minus n pi and cosine n pi are exactly the same, because cosine is an even function. Then we get this result. So Bn is given by this result. So now we know that this value changes changes between 1 and minus 1, okay? Why? Because when n equals 0, for instance, because n is running from 0 to, okay, infinity, don't forget, okay, n is, for Bn, let's check, So for Bn, okay, the function now is just from n equals 1 to infinity. Okay, so when n equals 1, n equals 0 corresponds to a0, by the way. So okay, so for n equals 1, we have cosine pi, which is minus 1. Okay, but for n equals 2, we have cosine 2 pi, which is 0. For n equals 3, it's minus 1 again. It's either minus 1 or 0, okay, depending on the value of n. And then we see that if this is minus 1, it gives you 2, so that this is equal to 4k over n pi when n is, okay, odd. When n is odd, not even, okay, Bn value is given by that. So since B is 0 for n equals n is odd, then the function can be written as, remember that it was changing from 1 to infinity, but n will change from 1, 3, 5 to infinity. So this shows that only the odd values are considered. In this case, Bn is just this function, 4k over n pi, okay, and the function itself, and the function is just Bn times sine nx, right? Sine nx, okay. Now we can run this thing on this, so we can see that if we do this, 4k over pi, which is constant, and the rest changes by sine nx over n. But now it's this sine x, okay, because n equals 1 gives you this sine x plus 1 over 3, okay, sine 3x plus, okay, 1 over 5 sine 5x, and so on. Infinitely many terms. Now what's happening? What's happening is this. Square wave actually is considered as the sum of all these functions. So the first one is just sine x, which is this, okay? So this is it. So this is the first approximation of this first term. If we look at, if we add the second term to it, we will have this kind of function like that, okay? So as you see, we are getting closer and closer to square wave. And if we add the third term and also fifth term, okay, sixth term, seventh term, we will just get some little oscillations and then maybe overshoots on the edges. And then if you get enough number of terms, this square wave can be really approximated with just a little oscillations in the corners and then total square wave. This is how you can do the analysis. So as you see, these are harmonics of this square wave. So square wave has many harmonics. So so whatever the frequency is, twice as much the frequency, 3 times, okay, 1 times, 3 times, 5 times the frequencies, the function will have this kind of periodicity. Okay. Now let's try to see if the vision comes back again. Okay. Let me play with this thing. Okay. Let's stop this recording and then start another recording later after fixing this.